Gravity on the Earth's surface is the resultant of gravitational and centrifugal forces. Due to the oblate shape of the rotating Earth, the gravitational force at the geographic poles becomes higher. The surface of equal gravity potential has a very complex shape called the geoid. Positive gravitational anomalies of gravity often indicate hidden deposits of dense ores.
You know, we're all taught in school that gravity is a constant. But what if I told you that wasn't quite true? That your weight isn't actually fixed, that you would weigh measurably less at the equator than you would at the North Pole? In this analysis, we're going to move beyond those textbook simplifications. We'll explore the fascinating, subtle variations in Earth's gravitational field and uncover what they reveal about the deep structure and the dynamic processes of our planet.
Ah yes, 9.80665 meters per second squared. You've probably seen this number 1,000 times. It's often presented as this unshakable foundation of classical mechanics, the standard value for Earth's gravitational acceleration. But here's the thing. This number, as precise as it looks, is not the whole truth. It's really just a globally averaged value, a convenient simplification of a much more complex physical reality. So the big question is, can we really use this one number for the entire planet? Well, the truth is, Earth's gravity isn't uniform at all. It's a dynamic field, and it varies measurably depending on where you are standing. To really understand why, we first have to deconstruct the very forces that we lump together and just call gravity.
You see, what we experience as the force of gravity isn't one single fundamental force. It's actually the net result, the combined effect, of two completely distinct forces that are acting on every object on the surface. We have pure gravitational attraction on one hand and the centrifugal force from our planet's rotation on the other. Okay, let's picture this. Gravitational attraction is pulling you straight down, directly toward Earth's center of mass. At the same time, centrifugal force, which is really just an artifact of Earth's daily spin, is trying to push you outward. The gravity that we actually feel and measure is the net effect of these two competing forces. It's like a cosmic tug of war. The resulting force, what physicists call the resultant vector, is what determines not just how much you weigh, but also the precise direction of down.
And this table here really highlights the critical difference. Look at the directions. The vector for gravitational attraction always points to the center of mass, no matter where you are. But the centrifugal force vector points outward, perpendicular to the axis of rotation. This means that it's only at the equator where these two forces are in direct opposition. Everywhere else, that centrifugal force is pulling at a slight angle, which not only reduces your weight, but also subtly changes the local definition of what down is.
All right, so we've got the theory down. Now let's quantify this. Let's look at how the interplay of these two forces, combined with the Earth's actual geometric shape, creates the largest and most predictable gravity variations that we see across the globe. This number, 5.2 centimeters per second squared, might seem small, but it represents the total difference in gravitational acceleration between the poles and the equator. To put that in perspective, if you weighed 150 pounds at the equator, you'd weigh about half a pound more at the North Pole. That's a significant, easily measurable difference. So what exactly is causing it? Well, it turns out there are two main physical causes for this variation. The Earth's rotation, which is what generates that centrifugal force we talked about, is the dominant factor. It accounts for about 2/3 of the total difference, or 3.4 centimeters per second squared. The planet's actual shape, believe it or not, accounts for the other third, or about 1.8 centimeters per second squared. Right, so the Earth isn't a perfect sphere. Because it's spinning, it bulges out a bit at the equator and gets slightly flattened at the poles. We call this shape an oblate spheroid. What this means is, if you're standing at the equator, you are physically farther away from the planet's center of mass. And as Newton's law of universal gravitation tells us, gravitational force gets weaker with distance. This increased distance is what accounts for that remaining 1/3 of the gravity difference.
But here's where it gets really interesting. This simple model of a spinning, slightly squashed sphere, it's just the beginning of the story. The real Earth is far more complex. It's got rugged topography and an uneven distribution of mass hiding just beneath our feet. And that means its gravitational field is equally complex. So, when geophysicists go out and make incredibly precise gravity measurements, the numbers almost never match the theoretical value you'd expect for that latitude on a perfect ellipsoid. These little deviations are what we call gravitational anomalies, and they contain a ton of information about what's going on in the subsurface. But to study them, we first have to apply a series of corrections.
Think of it like trying to hear a faint signal through a lot of static noise. We have to remove the predictable noise first. The free air correction accounts for your elevation. Obviously, the higher up you go, the weaker gravity gets. Then, the Booger correction subtracts the gravitational pull of the rock mass you might be standing on, like a mountain. Once you've stripped away these big topographic effects, what's left behind are the true anomalies, the subtle gravity variations caused by differences in density deep within the Earth's crust and mantle.
Now, once we apply all these corrections to a global data set of gravity measurements, we can start to build a map of Earth's true gravitational field. And this map takes us far beyond the simple models of a sphere or an ellipsoid.
And that's the key takeaway here. The models we use, they're essential tools for understanding the basics, but they are not the reality. The reality of our planet's gravity isn't a smooth, simple geometric shape. It's a complex surface that is defined by the very force it represents, a surface of equal gravitational potential.
And this is it. It's called the geoid. This is a model of the Earth's true gravitational shape. It represents the surface where gravitational potential is the same everywhere. The best way to imagine it is if the oceans could settle completely under gravity alone, with no tides or currents. This is the shape they would form. And we can even extend that surface hypothetically through the continents. As you can see, it's not a smooth sphere. It's a lumpy, irregular form that's often nicknamed the Earth potato.
So what are all these bumps and dips? Well, they're direct reflections of mass distribution underground. The hills on the geode show us regions of higher than average density, maybe something like dense mantle plumes. The valleys indicate mass deficits. And we can map this surface with incredible precision today, thanks to satellite missions like GRACE and GOES, which measure tiny changes in their own orbits as they fly through these gravitational variations, giving us an entirely new way to see inside our planet.
But the complexity doesn't even end with this static, lumpy shape. The Earth's gravitational field isn't fixed in stone. It is constantly changing over measurable timescales. You know, the gravitational pull of the moon and the sun actually causes the solid Earth itself to bulge and deform in daily tides, but we can now detect even longer-term persistent shifts. For instance, as the massive ice sheet in Greenland melts, all that mass gets redistributed into the oceans, and our satellites can actually measure the corresponding decrease in the local gravity field over Greenland. It's incredible.
So this is all fascinating science, but what's the practical application? Well, by being able to precisely measure these intricate spatial and temporal variations in gravity, we gain an incredibly powerful tool for peering deep inside the Earth without ever having to dig.
This really illustrates the power of what we call gravimetry, especially in resource exploration. After you've made all your corrections, a positive anomaly, an area where gravity is stronger than expected, can point you towards dense, valuable metallic ores, like iron or copper. On the flip side, a negative anomaly can reveal low-density geological structures, like salt domes, which are often prime targets because they can act as traps for oil and natural gas deposits.
So in short, we've taken a journey from a single, simple number to this incredibly complex and dynamic field. We now understand that Earth's gravity isn't some static constant. It's a composite force shaped by our planet's spin and its form, sculpted by the uneven distribution of its mass, and constantly changing in response to planetary processes. It's truly a window into the very heart of our world.
And this leaves us with a really provocative final question. As our ability to measure gravity gets more and more precise, what other secrets is our planet going to reveal? Could we one day monitor the movement of magma beneath a volcano? Or maybe even predict earthquakes by tracking the tiny gravitational changes caused by stress building up in tectonic plates? The possibilities are as profound as the force itself.
Thank you, friends. Strive for understanding and become wiser. See you soon.